The broadcast is now starting. All attendees are in listen-only mode.
Okay, good morning, good afternoon, good evening, wherever you are in different parts of the world. This is Krishna Vidula from IUCE and IFES. We're delighted that you have joined us for yet another fantastic, very interesting IFES webinar. In fact, it's now called the IFES GEDC webinar because GEDC has become an active partner in our conversations. So we have with us Mahir Futuhi. He's the regional manager for Quanster, which is many of you already know that company, very famous around the world for some exciting technology that they've been developing for educational and for other industry purposes. Topic very provocative. Tomorrow, everything will be able to see, think, and do, and communicate with everything else. And Mahir is going to tell a little bit about how that's going to work. And so I'm going to make Mahir as the presenter. And we'll take it from there. Let's see, Mahir, presenter, click, and now Mahir has to click show my screen. Okay, go ahead, Mahir, show your screen, and then you might put up your face a little bit for a minute or so, 30 seconds while you introduce yourself. There you go, we can see you.
Hi. Good morning or good afternoon, everyone, depending on where in the world you're logging in. My name is Mahir from Quanster. I look after universities in Asia, Middle East, and Europe. And today, for the next 30 minutes or so, I will share some of our experience from working with various universities across the globe in the new era of modern engineering education. So if you don't mind, I'm actually gonna stop the video for the smoother experience. I believe you still have the screen, correct?
Correct.
Okay. All right, let's dive into that.
On the bottom of the screen on the left, you can move it back and forth. Yeah, there you go.
All right. The name Quanster is the combination of question and answer, which indicates the academic origins of the company. Now, I think everyone agrees society and specifically the engineering world has changed significantly over the past few decades. And the question of how do we maintain the relevance within our program and how do we prepare students to succeed in the world of new technologies has become a very challenging question. So basically, that's the question that we would like to address in this session, which we all know is well beyond that, but we're going to have a good attempt to cover the majority. So Quanster initially started off as an expert in the field of controls fundamental. But over years, we evolved to mechatronics, robotics, and last but not least, complex intelligent system, which is obviously the topic of this session. So when considering the many challenges of curriculum's transformation for these modern application area, we have gravitated towards three different set of activities. First is the idea of engaging and adopting with the new generation who are already immersed in the complex and digitized world. We need to not only respond to that, but also leverage that familiarity to maximize the education effect. Second is to rethink the way that we are teaching design, in a sense that design projects are more than aligned with real complexity and application and system level, which is demanded by modern industrial world, which brings us to actually the third option or third point, which is to better align in terms of skill set and outcome to those requirements that companies all around the world is screaming for as they try to align themselves as well. So we can imagine this can become a complex loop. Now, the core element of any education transformation absolutely has to deal with the real life application. And when you think about what kind of things that are really commonplace and certainly within the imagination of our students, it really begins to show how tricky this is going to be. One of the things that we have done is to really think about the clarification or demystification of this approach. The approach that is accurate enough about the application, a complex application, but also in a way that you as a faculty member can implement it into your classroom. And just as important as that, obviously, is our average student can fundamentally appreciate and function within that class. Now, this diagram is an example of how we at Quanser taken a broad category of modern intelligence systems and propose a way to think about it. At the center of the diagram is a physical system. Again, any real life application has to be seriously considered for the complex engineering approach, because as an engineer, we're not only interested in coding and programming, but also real life implication of those topics. In today's world, we can assume a physical system. Okay, I apologize. I think, yes, sorry about that. Yeah, basically the idea here is that in today's world, we can assume any physical system can have some level of 4 categories in some extent. It's seeing, thinking, chatting, and doing. And in a more technical term, sensors, computation, actuators, and communication. This simple categorization has become a very effective way for us to develop application and methodology to teach, but also to communicate how you implement them in the classroom, and has become a very useful tool for a broad range of activities on the campus. So we're going to see a sequence of different experiences, all based on the same piece of lab equipment, in this case called Quanser Cube 2 servo motor, which is a servo motor that has a little bit of expandability. We're going to start with the most natural starting point in any engineering system, which is physical system at the core of the diagram. In this type of example, you're going to see how this type of device is going to hold this. We always have done quite well in the academic world when it comes to engineering system. So have a look. What you can see in this video is a very effective way of showing the balance of a rigid body. And in fact, it is very typical of the kind of activities that the students see in their controls courses, and they have seen that for the past decade or so, or even more. They experience various forms of model development, simulation, and techniques to deploy that while looking at real-world aspects of dealing with a relatively sophisticated inverted pendulum system. Now, as well as obviously the technique that need to deploy those techniques. So we believe once the students are able to do this, then they have a good understanding of fundamental of controls. This is a classic experiment, very well known, still very effective, and we have to remember this is basically a ABCD of a complex engineering system. Now, let's move forward. As you know, it's common these days to find more makerspaces, or sometimes they call them innovation hubs, different in the countries, different names, which is conveniently available to most of students, fortunately. But it's actually not easy to create a meaningful project for a student in order to experience the true academic complexity design that we talked about previously for a modern application. There is some sort of a disconnect here. In this example, we're going to explore the do or the actuation aspects of our framework and show that how we have combined the creative aspect of market space with the traditional physical system. So this example shows the merging of a makerspace activity with a more traditional high precision control of dynamic system. As you can see, you have the servo motor, the base, the same unit that was used to balance the pendulum. And the student designed a 3D printed golf arm or shooter to shoot the ball into the cup. And obviously they have the parameters, the distance, the velocity, the input to the motor. So it becomes a very nice challenge to solve. How are you going to actuate the motor to get to your objective, which is shooting the ball in the cup? So it's basically projects like this, which shows that with the exact same device, same base unit, and a little bit of creativity, you can move makerspace above, beyond simply creating some projects, the things that are very strongly aligned with the modern precision application. The next, we will look at application that one may consider actually a more advanced mechatronic system, where we begin to explore different type of sensor techniques and sensor integration, where the system becomes much smarter. It has the ability to sense or see. In this case, we're going to take the exact same servo motor and going to modify its ability to sense its surrounding and also create a meaningful application in a way that is a little bit more fun and engaging for a modern student. So let's have a look. And here you're able to see the camera, the motion detection camera, which is a Microsoft Kinect right here. And at the very beginning, they sense the motion of the student arm, and then the computational part is going to translate this motion to input signal value and becomes a complete control system, feed it back to the motor, and eventually balance the pendulum. As we saw before, this is again the exact inverted pendulum application, but the input is now much more sophisticated here, and in many ways much more fun or relatable for students, compared to simply putting in the signal value through the software. And needless to say, this way student can experience a much more sophisticated approach to complex engineering design, but in a very more modern take and approach. Now, in this example, we're going to move on to an area which is very relevant and important these days, which is the area of IoT, Internet of Things, and the cyber security. And in particular, we're just what we did before. We're going to do the same complex physical system, but we connect them in a way that they have a combined function as an entire system to accomplish a mission in coordination. And then we're going to try to disrupt it intentionally while exploring the engineering concept we need to know to keep everything functioning properly. And in this way, we're going to explore the chat or communication side of the framework. Let's have a look. So there are two servo motors with the embedded pendulum attached. And at the very beginning, I'm going to run the video, they are working independently. As you can see, there is no connection to independent system. Then the system is connected through the cloud server, which means that you have a leader on the left, a follower on the right. As you can see, the follower leads, and then an error in the communication channel, cybersecurity threat, and the piece of code that the student has written. They're trying to solve this, stabilize the system, bring it back up. System works just like before. Leader is leading the follower. And by doing this, we are covering the key architectural elements of a modern cybersecurity of connected physical system. Again, based on the same building module, but a totally different, relevant, but very important application, modern application. Now, finally, we're going to move to one of topics which is arguably the hottest amongst engineering field these days, and that's the area of AI and machine learning. We're going to take the same hardware platform, the servo, in the inverted pendulum mode, and we're going to explore the think side of the things, and that's how we do more advanced computation, so that the traditional approaches, such as, let's say, mathematics and modeling, are now combined with the statistics and basic decision and learning techniques or machine learning. So all of these key and trending topics that are coming out of computer engineering world are now implemented in a physical, real-world system. So the actual application is stabilizing or a stabilizer for inverted pendulum, just like what we saw before. Now, the first thing we need to do, basically, we need to measure a bunch of sensory information, such as angle, velocity, encoder, and so forth. And then what we can do, we can use, which is a traditional approach, some sophisticated calculus, differential, different state model to calculate some values as an input to the system. And once we figure this out, once we do the right technique, the system is able to work in real-life communication and real-time communication. Therefore, the system is stabilized. This is some sort of a traditional approach. Again, it's very important to give us the base. But there is a major problem with this classic approach, a mathematical approach. The reason is that the system can get fairly complex. Now, we have a relatively simple inverted pendulum compared to what we see in real life, and even that can get fairly complex. How do you define that system? Basically, the mathematical phase is extremely difficult. In many cases, we don't have the actual math and computational techniques to get the right set of equation. And this is a problem that AI is approaching to give us some alternative. In other words, ironically, AI starts with a much more ill-defined or looser approach. Rather than coming up with a more precise mathematical model, it actually goes through various trial run as many as possible, then compares the results, and using different techniques, for example, machine learning, eventually converges to the right parameters. And this is a huge step forward in complex system, that we don't know the actual parameters value, neither the way to define those parameters to begin with. Now, this sounds very complicated, doesn't it? Going through a bunch of loose models, iteration, various iteration, massive number of iteration, because actually it is. It's very demanding. But considering the collective knowledge these days, and also the abundance of computational power, it's become possible. But not only researchers that have access to supercomputers, but also undergraduates to take on such an approach, such a challenge. this is some of the work that we have been doing, which is basically to take the same application but apply an AI treatment to solve this issue. So the next video is going to show 3 different approaches to stabilize an embedded pendulum, one of which is AI. Let's have a look. You have 3 models at the very left. It's a classic approach, analytical model, that we know the model to some extent because we designed the solution, so it's not hard to figure out at this point. We know the model, we have a sense of parameters, we command the system, works beautifully. The second one is something called system identification, which is a statistical technique. It means that you have an idea of the system, the parameters, and you allow computer to estimate that. And obviously it does not work in this case. Now, what we have on the right, which is where the magic is, they have designed, again, using AI, an algorithm that starts with a rough estimate of the model, but over time, after various tries, it converges to set of parameters that manages to balance the pendulum. And one of the reasons that this is done these days, and it gets the job done, is using some emerging tools. For example, open source Python, or some more structured and commercial tools such as MathWorks and Simulink these days allow you to put together that algorithm relatively quickly so that you can do things like this. Now, I'm going to change gear a bit to more application, one of the trending application, which is unmanned system or aerial vehicles, an area that Quasar has been very active for the past decade or so. And over time, we have gotten to the point that what actually keeps us busy is not only how to teach students to stabilize, localize, and command these agents for unmanned system. Our goal is how to teach to design such a complex system, which again, that's another real life and trending application. One example that I would like to share is working with American University of Sharjah in UAE, Dubai, to define an undergraduate program, which is an intensive, compact program, sprint-like program for drone design. And the students get to understand and learn about the subsystem, and they get to assess each subsystem and eventually being able to understand the design and eventually even control the system. So many different techniques to cover in such a incredibly complex system that students need to learn, which is obviously beyond actual skills of assembly and so forth. We're talking about concepts such as foundation, design, research, and automation application, and manufacturing, commercialization, which on its own is a separate field. Now, I would like to talk a little bit about the practical platform for fairly quick integration of academic program in the area of the smart system, which is, again, that's the topic of our focus here. And to do that, I think the best way is to go over an example of what we have recently done with a leading university in Canada, McMaster University. They have taken on the challenge of defining the pivot concept, which is basically restructuring undergraduate courses, all the undergraduate courses, from the very beginning, from the first year, at the very entry to the classroom, all the way to the 4th year. And this has been done for answering this question. And one of the things that we have to bear in mind, going to, again, what we talked before, is students are technologically savvy, they're hands-on, they're motivated these days, and that's an asset. We need to invest in that asset. We need to try to get the most out of that asset. So that was one of the things that we had in mind when it comes to designing or restructuring their program from ground up. Now, Quanser contribution is to reimagine the sequence of how we teach. Again, project 0, at the very beginning, the moment that they walk into the door, all the way to the last year. They are in the specific example or project, there are 5 different projects. You start with the project 0, which is Introduction to Smart System. And I think that's really exciting for students, because rather than jumping into theory and some of the abstract concepts, which could be boring, not only you're engaged, but more importantly, you have a context. When you go to project 1, 2, 3, and 4, you have a high level understanding of what a smart system is and how exciting it can be in order to be able to design one. Then you move to project 1, which basically dives into the basic fundamentals: sensor information, computation, program, and material science. And you will see why this material science and the sensor actually is important for this project. So let's have a look at the second project, which is actually a fairly complex challenge. The students learn to control a robot arm, not only by inputting signal, but also by commanding the robot to sync with their hand motion using my electric signal, which again adds another complex but important and meaningful challenge to the project. The third project, or actually the fourth project, project 3, is all about architecting and designing a complex smart system application. That's where things come together. You have the robot arm, mechanical side, the electric side, you have the sensor information, you have a smart system, a moving agent, you have operators. Now the question becomes how you architect the system in order to create a meaningful application. That again is a real life challenge. Project 4, there's some open-ended challenges there that can be changed and defined. Now, as an example of the project 3, which is a smart recycle sorting system, good example of Industry 4.0. This is a little nice sketch of what the elements are. You have moving agents, the Quanser robot, you have a servo, which is able to command the circle, the tray. You have the robot, which in order to get there, the student have to understand robotics principle, mechanics of the robot, modeling, and so forth. And also you have material science. And then they have to wrap a meaningful application around each sub-item and deliver on the master vision of this project, which is getting them all coordinated to deliver on the mission of recycling, smart recycling. Now, one thing I need to mention, the approach here was not necessarily to design a very complex system from ground up, from the very, very beginning. We know that's actually not a real world, because when you look at companies, how industry actually works, you have many companies that each of them are expert in one of these subsystems, right? So at this point, we don't want the students to be immersed in one vertical and go very, very deep. Right? We want them to have this understanding of the system level, but also be able to design and improve each of these subsystems, and then eventually connect them together to be able to do the final objective. Now, this is the video that shows the project. This project is going to be live in fall 2020, but we have put together this video to show the concept. You can see after the sensor review of each bottle, the robot picks the bottle that needs to be picked, and the Qbot, which is a Quanser grounded agent, is able to navigate, considering the code, the piece of code that has been written by a student, to the right box and deliver the right bottle to the right area for recycling. And another concept here is basically the idea of digital twin, which means that you are able to actually integrate a high fidelity digital model with a hardware to work in parallel, and you can create some sort of a quasi virtual environment, which, or augmented reality, which is a combination of a hardware with one of these virtual models that you see that in this video to work in a coordinated way. And that was actually another part of the program that was pretty novel. Yes, I mean, we had a chance to talk about McMaster, University of Sharjah. We have partnered with University of Mexico in USA. And the good news is that we believe this is a truly global trend. There are various other universities that we have engaged to tackle the same challenge, which is basically how to prepare our students for a complex application-based engineering design, and this is growing. Thank you very much. I appreciate your time, and would be happy to answer any question you may have.
Fantastic, Maria. This is fascinating, very thought-provoking, and highly appreciated. I think it's great. I think a lot of relevance to engineering education, as you have pointed out. So we have about 55, 60 people here, some from industry, but mostly from academia. And I'm sure they're all, each and all, well, have some questions for you. So I'm going to ask folks to just text saying, I have a question. I can unmute you so you can have a actual conversation if you want to do that, or you can just text a question or comment as you wish. So let's get started. Okay, so in the meantime, I'm going to see if Hans has a few comments to make. I just had unmuted him because some disturbance coming along.
Thank you very much. I'm having some technical difficulties, but just shortly, we deeply value the partnership with Quanser and the creative outreach that you are describing. It's very interesting to see on the map that most of your partners in the different parts of the world, including Sharjah, where our new GC dean is assuming the dean position this Saturday, McMaster, University of New Mexico, Tsinghua University. I can go down the list. It's beautiful to see the broad network of university connectivity that Quanser, all of you have built. And I just wanted to express my thank you and again for your giving this webinar this morning. Thank you kindly, Krishna.
Okay, thank you, Hans. I'm going to go into some questions here. I noticed Ala is here, the dean from American University of Dubai. Maybe he might have some questions. I'm going to see if he has some. Doru from Romania is here. We have various people here from different parts of the world. So don't be shy. We have time. That's the main reason why we keep this extra time, so we can have interaction. Because as you know, that unless we have interaction, we don't learn anything. Just listening to a talk. So let's. We've got Sanjay Godalai from India, and various other people there. So I'm going to start with Anil, and maybe go to some of the others. Anil had a quick comment. Anil Kumar Pandit from India. Would you like to make a comment? And after that, we'll go to some of the others. Anil?
Oh yeah, sure. This is Anil. Hope you can hear me.
Yeah.
Yes.
Okay. Yeah, this is a great presentation, really. I must say, demystifying the industrial system and scenarios, its complexity is, I think, a wonderful way to start. And as I see it, Quasar will really help students to even reach quasars and pulsars in the celestial domain.
Okay.
Yeah, okay, that's it.
Okay, good. Let's go to Ala. Would you like to make any comments, Ala? I'm going to unmute you, Ala.
Sure. Yeah, thank you. Thank you very much for the interesting presentation. What I want to, it's not a question, but maybe you can shed a little bit more light on the driverless autonomous vehicle systems that you guys are putting together and putting out in the market very soon. Because I'll be talking to a few people, Paul and Tom, regarding this, and we're interested in acquiring these. So hopefully we'll be working with Quanzer on this. But I thought maybe you wanted to highlight that product little more.
Definitely, and thank you for your comment and interest. So the Q car, that's what we call it, which is actually the most exciting project in 2020 for us, is basically more or less conceptually the same approach. When we look at the physical system, we have designed a system that has chat, see, do, and think in actually a lot more depth. Basically, the same concept of demystification is applicable to Q car. Now, without going to the technicality of the details and feature set, but we believe that is the most effective way of teaching unmanned system, complex unmanned system with this model. And that product is designed to optimize each of these sub-department, all the way from the see, chat, do, think, and obviously the physical system. And one of the things that, again, needless to say, is a massive trend is driverless car. We believe we can demystify driverless car embodied in that physical system that we have designed, which is composed of, again, various subsystems. And one of the things that we are excited about is basically be able to roll that out and enable the students and teachers to have the understanding of unmanned system, because that by definition is very important and fairly complex, because it's basically taking whatever I showed here to the next level and beyond that. So we know it's a big challenge. As you mentioned, this product will be released early 2020, which would be in a month or two. We already have some our first customer from RMIT in Australia. Actually, they acquired the system even before the release, because they had the mandate to make that happen, and it's practically the only solution that one can find. So we are very excited about it, and I would be happy to actually follow up with you about the development of this project. But to just summarize again, it's the embody of what we see here for subsystem with the niche application of wireless system, driverless cars.
Okay. Any follow-up, Ala?
No, just thank you. Wonderful. We're looking forward to working with you on this, Mahir.
Okay, thank you, Ala.
Not a problem.
I'm going to go to Doru from Romania. He has made some statements. Let him talk for himself. Doru, come in.
Hello, you hear me?
Yes, we can hear you, Doru.
Okay. First of all, I want to thanks to Paul and all the team from Quanzer for the good devices they built. Second, in my university, in my department, and in my laboratory, we use mechatronic system for near-this from Quanzer. And from the moment when we introduced these systems, all the students was very happy and learn better. This is absolutely clear. My question is, I hope that in this presentation to see more information about sensors, about how integrated sensor in this mechatronic systems. And one special question, if Quanzer start to use Li-Fi in their system, because now it's a lot of companies, a lot of teams work to use Li-Fi communication for the systems.
Sure. Thank you for the comment first. And so basically, you have it seems that first you have some experience with working with Quanzer solution. And your question, I believe the first one was a little bit more information about the sensor. Are we talking about the sensor when it comes to cube servo, or the sensor side of the equation general?
No, my interest is about the sensor, how we can integrate in these systems the sensors. Because when we speak about IoT, we must think of industrial IoT, medical IoT, and so on. And in all these cases, we discuss about a huge number of sensors.
Yes. That's I see. That's a good question. So if I go back to the one slide that had multiple agents here, right? For example, I mean, technically in this example, each device has one encoder to measure. It has one, actually two encoders for the rod and the base to measure, to just keep it simple, and actually a bunch of IOs that it can be expanded. So in this example, we're talking about, to begin with, we have 16 sensors. But I think your point is that when it comes to connected devices, sometimes we're talking about 16 times 10, 100, 1,000, and that itself is another level. Now, if I go back to the video that we have 4 drones, now the number of sensors here are much more, right? But one thing I need to mention here, each of these agents, for example, that can be grounded as well, they have a board on each device, which are expandable. So they have a bunch of IOs. It can start all the way from 2 to 32 IOs, digital or analog. And that gives you the expandability, because technically we know this in grand scheme, this could be limited as what you refer to. So we have given this option to expand the sensors and feed that through MATLAB Simulink or whatever software they're using in order to be able to address a wider range of sensors. That has been our approach so far. So basically, even though we're going with the sensor that is built into the device, we have designed the platform that is easily expandable for the researcher or teacher to add their own sensors, because we know when it comes to IoT, we're talking about much more sensors. And there are even actually boards that I didn't get a chance to get in and look into that comes with the cube that makes it more expandable, that you can read the information from any analog device, or even add it to your Arduino and feed more sensor temperatures or whatever it is to the Simulink and design your controller around that.
Okay, great. Thanks, Doro. I'm going to move on to the next question from Archana from India, Archana Bhange. Would you like to speak for yourself, Archana? You had a question? Go ahead, come in. I've unmuted you. Otherwise, I'll just have to ask a question. Okay, she is talking about the Quanser help in establishing such labs or projects at various campuses. So how does that work? I mean, what's the, somebody's interested, what do they do, and so on. I noticed you have 1 or 2 in India already. And this other one is also a question from India. So you want to explain a little bit about that process and what it takes?
Sure. So very good question, because, you know, as you probably can see from the theme of the presentation session, is we have been trying to develop a framework that is replicable to different contexts. Again, if I go back to the classic side, you know, ChatC thing, we believe this is the way that we found it very effective to communicate not only to the faculty but the students. So going back to how we go about implementing such a project, we always start with the vision for that department or that school, and sometimes we help to craft something together in order to come up with that. But we know each university, each school have their own mandate, and you know, we find that sometimes application based. In case of AUS, it was unmanned system drones, right? In the case of McMaster, it was recycled because there was this mandate from the university or division for a cleaner environment, and to take a major step in that. So, but the good news is that whatever the vision or the mission is, based on this demystification approach, we have been able to actually put together a program, basically dissect that vision into executable subcontext that makes it digestible for a student, and also it makes it a flow that they can start from the very beginning to the final project. So the first step would be to get to know the vision for that institute. And then where Quanser can contribute is, again, the system to execute this sub-block in order to make it a flow, a meaningful flow for students from the day 1 to the final year. When to do that, obviously, it's a lot of communication. We need to sit down with yourself and whoever has vested interest to learn about. What we do the first is that what is a success? If we want to dream for this institute, how would you define the success in the application level and in the terms of what quality of students you want to graduate for some of these niche trending markets, and we work backwards from that to break it down to executable course level annual basis, if that makes sense.
Okay, great. Question from Felix, again from India. Felix, do you want to ask it yourself? I'll just unmute you if you feel like you have a mic, but if not, I will just read out your question. Come in, Felix. Okay, his question is, engineering systems are interdisciplinary, interconnecting domains of knowledge. And so obviously, do these projects require group teaching, right? That's his question. How do all these projects get guided and taught in these places? Group teaching, just interdisciplinary faculty, everybody gets involved. You might want to describe that a little bit.
Just I want to make sure I understand it. The question is that how do we go about group teaching the faculty when it comes
teaching, and also students, I guess, have to be from different disciplines, right, to work on these things. So you're really you're simulating the real world by having faculty with expertise in different areas teaching students who are on different disciplines and building a project, right? So you might want to talk a little bit about how that's working in some of the universities where it's happening.
Yes. So one thing we found, and this is, I'm just bringing this up because I've been only the observer of this trend, that some of the universities that are on the leading side or bleeding edge, the notion of the programs or have a rigid definition of different programs is going away. And I think, for example, in McMaster, it's all about an objective, the experiential learning to get you to that objective, right? And I know this could be a bold move for some, actually for most of universities, even tier 1 universities, is still very structured, they're different programs. So students have to pull in, they get to pull in from different programs. But one trend is that I believe this could be a disruption in the flow of teaching, that there's going to be a lot of gray zone in terms of program. Therefore, when it comes to group teaching students, you don't necessarily have to be limited in electrical department or mechanical department. You define a project which is real life, complex, and the students may choose to go through that project. And by pushing themselves through that project, then they have maybe at some point a weird mixture of electrical, mechanical, and chemical that is a huge asset, because we need such a person for real life and solving these grand challenges. So when it comes to grouping, one thing I find is this trend of basically a lot of students are in this gray zone. At some point, someone can say they're jack of all trades, this expression. But we do need that. We do need people who understand that. So therefore, when it comes to grouping people in some of these projects, there is not real definition. Obviously, these universities still do have mechanical, electrical, and so forth, but all the students are welcome to chime in and go through that experiential learning. One other thing that I would like to mention, we actually need, the other part of this that we didn't get a chance to talk about it, which I think is very important, is how to train the trainer. And when it comes to some universities, when it comes to managing the labs of various students in large numbers, that itself is actually a challenge that we're working on. That. How do we make sure this model is not lost in translation when it comes to executing it in various labs with various lab managers, right? Because one part of what we do is not only creating the content that helps educating the students, actually how to deploy that. And we found that we have to be on the top of that. So a part of this program is rigorous training of whoever is involved in deploying this, to make sure they have the right vision content, sometimes they need to have a separate content. You have content which is separate for lab manager and students, because at the end of the day, they're actually running the show and they have a lot of power in terms of making this happen. So that's another side of the group teaching or group training that we are working, which was not included in this, but I need to mention this is a big part of what we do most of the time.
Okay, great. Another faculty member has a similar question, but maybe he might want to address it anyway. Ashok Darshanala from India, would you like to make any comments, or has your question been answered by the recent question where you talked about other courses designed and the students and interdisciplinarity? If you think your question has not been answered, just go ahead and ask it again. Okay, so another question was, do you project 0 to project 4 maybe included, this is from Yadav from India, maybe include first year engineering? So is the 0, 1, 2, 3, and 4, I assume, are taught in first year, second year, third year, and fourth year? Is that how the projects are lined up typically?
Roughly speaking, yes. Yes. Okay. Now, and yeah, it's around 4 to 4.5, and some of the projects that they're actually at basically pass or fail phase that they have to go through. So if it's a fail, obviously they go back and they can add to the length of the program to make it 4.5, just like a realistic, program. But roughly speaking, it's designed for 4 years. Yes. Okay.
Another question from Praveen is. Has to do with, I guess, his computer engineering department in India somewhere. So how much of computer engineering is involved in these kinds of projects? Is that in terms, if you compare the relative amount of disciplinary topics within these projects, the computer engineers, I'm assuming, play a major role in these projects, right? And so it would motivate them to build real world engineering projects relevant to Industry 4.0. Would that be fair to say that?
Absolutely. And that's a very good point that we need to all be aware of, especially if I'm coming from mechatronics and control system. The reality is that conventional, again, 20, 30 years ago, control system was, if I'm coming from control system background, so I'm a little bit biased, I have to mention that. But over time, I realized in order to do these great things in the world, to solve this complex engineering challenge, actually, the game changer could be out of controls, right? Because controls, modeling, dynamics, we have done that for 20, 30 years. They're classified. Everyone knows. They have computers that they do the modeling, What makes it the big change here is actually what was mentioned in the question. We believe, and that's the thing part, and that is, as mentioned, is one of the most hot topic, and there's a reason to do that, because we believe if we figure this out, not only on the industrial level, on the research and teaching level, then we are talking about exponential growth in terms of solving the problems, the grand challenges. We saw a hint of the statistical model and AI and machine learning. And the reason that actually we're able to do things like that is because of rapid development on this side of the computational side of the question, in terms of the computer science, the algorithm, and also the computation power. So if I actually were to pick one among all these 4 or 5, I would put my bet on this, because this has the most radical changes. You guys definitely know about the big data, AI, deep learning that we talked about. And one thing which is really exciting, 3 years ago, we were not able to do this. This is the simple demo, right? But this is an indicator of what is coming, the velocity and the magnitude of the change that is coming from the computation. So absolutely, computational. And I think that's a very important point, because most of us who are coming from different backgrounds, we are somewhat biased towards that. But we have to, in my personal opinion, I have to be very aware of what's going on in the computational side, because that's the subsegment that's going to have a radical change to bring everything together and make an impact.
Great. We've run out of questions, but I'm going to see if my friend Sanjay Gadale wants to say anything. He's self-muted. I don't know if he has a mic. Sanjay, do you want any comments from your end, or you not have a?
I
comment.
I actually had to join in a little bit late because I was driving. So in fact, I'm very thrilled by this entire presentation. I think I will catch up with it on the recording. Maybe I'll catch up on the mail afterwards.
Okay, great. Okay, thank you, Sanjay. And okay, good. Looks like the fantastic job here, Maya. Thank you for your time. And we had some very nice questions. And thank you for the audience. And again, I remind the audience that we are here to have discussion and not just give you a lecture. That's why we keep the lecture to 30 minutes so that each of you does have a chance. So come prepared, with wanting to be able to ask questions, and even if you come prepared with a mic, so you can actually speak, because I can unmute you. So it's exciting. So thank you very much, Mahir, and thank you everybody for joining us, and thank you IFES and GEDC, and see you again in a couple of weeks.
Thank you very much. You're more than welcome. I really enjoyed the conversation. Thank you.
Okay. Anything from you, Hans?
Well, many thanks. I deeply value the partnership and the very, very professional presentation that you've given to all of us. It's a complex, fascinating subject, and I look forward to discuss this further. Thank you so much.
Okay, take care, everybody.
Thank you, Hans.